Okay, assalamu alaikum everyone. And today we'll continue with our fourth lecture on microelectronic design. So we will finalize the last two topologies which we want to cover, the common gate and the source follower. And then we will have examples in all the circuits that we had so far. So we'll try to solve some examples in order to become more familiar of finding the gain. And any point you have any question, please raise your hand and we'll get your question so that you don't get lost somewhere, okay? So this is the common gate circuit that we discussed it earlier. So we have the input coming at the source side and the output is taken from the drain. Okay, so this is how you should identify that this is a common gate circuit, and the gain of a common gate is a positive non-inverting topology with the gain given by GMRD. Here we'll always assume that in the common gate stage that lambda equals to 0. So this is, we always make this assumption just to make life easier for the calculations. Okay, and we last time derived the gain, so today we will find the input and the output impedance of this amplifier. Okay. So basically, in order to find the input impedance, you will apply a test source at the input side. That is value Vx with the current coming out is called Ix. And then we will find Vx over Ix. So let's do this. So now Ix here, you can see how Ix is related to GMV1. There are two currents going in the same branch, and both of them they are in opposite direction, but they will have equal value. Okay, so Ix equals minus GM times V1. And V1, how is V1 related to Ix? They are both, this is from this point to ground, but this is taking a negative sign here and this has a positive sign here. So Vx will equal to minus V1 or V1 equal to minus Vx. Okay, and then if I just change this quickly, so I will have Ix equals minus Gm multiplied with a minus Vx, and therefore Vx over Ix will equal 1 over Gm. And this is the Rn of this amplifier. Okay, now just get the light behind me turned off and come back 1 second. Okay. So now what we are going to do is to find the output impedance. In the case of the output impedance, we will first, as we discussed earlier, short the input, and we will apply a test source from the output side that also has a Vx value and current coming out Ix. So now Vx, yeah, but first of all, what about V1 and GMV1? What is the value of V1 here? Both sides of V1, this side and this side, they are both grounded. Therefore, V1 will equal to 0. Why? Again, because both sides of it are being grounded. Now, this will make the G and V1 current source will equal to 0. V1 is, because V1 is 0, so this is like an open circuit, no current is coming here. So all Ix will go into RD path. Okay, so Vx will equal to RD times Ix. Again, because all the current will go into RD, nothing is going into that direction because V1 is equal to 0, and this makes the current source GMV1 as not existent. So Vx over Ix will equal to RD, and this is the R out of the common gate amplifier. You can see that here, and from the output side, it's really, I mean, somehow similar to the common source amplifier. Any question on this? Okay, we can move forward. So these are that we derived earlier, that input. You can see that it have a low input impedance. And therefore, it's just for your information, it can be used for, if our input is a current, like a trans impedance, we call them trans impedance amplifier, it's preferable to use this topology because it has a low input impedance and the current likes to go in the low impedance path. So just for your information. And output impedance is equal to RD. Okay, now what will happen if my common gate stage has a source resistance, a resistance that is RS comes with Vn. So how the gain is going to be changed. Now you can think of this as like a kind of a two stages. The first is you go from Vn to this node Vx, and then from this Vx to the V output. Okay, so reaching from, so V out over Vn will equal to Vx over Vn times V out over Vx. Okay, like a two stage operation is happening. First, I go from Vn to Vx, and then from Vx to V out. So what is Vx over Vn? Now, if I look at this simplified diagram here, now this is my Vx. Now, from where this 1 over Gm came from? I know Vn is clear, Rs is clear, but where this 1 over Gm came from? It is the impedance that I am seeing looking into the amplifier. Okay, so at this point, there is an impedance on this side going. So what is this impedance? It is the input impedance of the amplifier, which we just derived earlier. It's 1 over Gm. So at point Vx, there is something that I see here looking up, which is the 1 over Gm that we simplified it and added here. It's like the entire amplifier is being just replaced with this resistor at this point. Okay. So now Vx over Vn, from here it's kind of a voltage divider. So Vx over Vn is equal to 1 over Gm divided by Rs plus 1 over Gm, a voltage divider. Okay, now this is the Vx. Now going from Vx, where I do it here, from Vx till V out, it's just like the common gate stage from the input till the output. And therefore V out over Vx will equal to the gain of the common gate, which is Gm Rd. So V out over Vn will equal to Vx over Vn, which is 1 over Gm plus Rs plus 1 over Gm, 1 obviously because I just have one transistor here, multiplied with a Gm1 times Rd, which can be simplified. This Gm1 goes with this Gm1 to Rd over Rs plus 1 over Gm1. What does this looks like? This gain reminds you of what? Does it remind you of anything?
I have a question.
Yes,
Ma'am,
please.
could you please explain what is Vx?
Vx is just, I gave this node a name. So it's not
Ma'am,
anything. Yes.
ma'am, why did we resolve V out over V in Vx over V in into V out over Vx?
Yeah,
Why
why
did we
we
just
did that? Because it's difficult if you want to do it directly. I
okay?
mean, now what has changed? This, there is an addition of this resistor Rs. So not entirely the Vn is reaching to Vs to Vx node. From this point, you can see it here, until this point, from this is node to this node, you have a gain of GMRD. But not all of Vn is being arrived at this particular node.
Oh, okay, ma'am. Okay. Thank you, ma'am. I got it.
Welcome. Yeah, so therefore we need to do it in two stages. First, we need to see how much of portion of Vn is arriving here. And then from here to here, that node, what is arriving at the source of the amplifier to what is being delivered to the drain of the amplifier is this gain is GMRD. But not all Vn is arrived at the source of the amplifier because of the addition of this source impedance resistance. Therefore, some, according to this voltage divider portion, is being delivered. And that's why the gain is being reduced from not the old GMRD, it's RD over RS plus 1 over GM. And this looks like the common source with degeneration stage. Only that was a negative sign. This is a positive sign. So the source, there was also a source impedance. Here, there is also an impedance. There is a resistance that is being seen at the source side as well. So they are the same equation, only the sign is different. Any other question? Okay. We will see this with one more at least example will come in this case, and we will see how we can also remember that you need a voltage divider. Okay, so this is how we did it. Now, if there is an impedance that is basically coming at the gate side of the amplifier, will this change anything? Let's see. So when the gate resistance is present, it does not affect the gain. Why? Again, because there is no current that goes into this direction. So there is no voltage drop across it at low frequencies, because here we are not considering that there is a gate capacitance. That's in a future. Okay, and also this point which we just mentioned earlier, that the impedance also that we see at the common gate, no, it's a different point. The output impedance now that we will look here, in case of having a source impedance, it will look like common source with degeneration. You remember that relation which was R out equals to R out plus GM R out RS plus RS. That was the impedance in case of the common source with degeneration. It will be the same here in the case of the common gate with the source resistance, and you can prove it. Why it's the same? I mean, from a derivation point of view, why we will end up in the same output? If you remember, because in the same case, when we will find the output impedance of the common gate, the first thing is that we are going to short the input. So I just want to we will short this side, and we will apply a test source from here, from the output side, Vx, with the current Ix. So shorting the input, it will again look like the common source with degeneration stage. So that's why we will end up with the same output. Any question on this?
Ma'am, I have a question.
Yes, sure.
Ma'am, you mentioned that we have to ignore lambda in common gate. So, ma'am,
Yes.
why did you add R not here?
Yeah, it's a very good question. I don't know why the book is doing this. One time it's remembering it, one time it does not remember it. I think they only just consider it for the case of the gain calculation, but they add it for the R out. Otherwise, it will be just an infinity. But your point is 100% valid, that sometimes it is there, sometimes it's not. And it makes it confusing. But I mean, whenever you do any solution, just make what is your assumption. if you are assuming lambda is infinity at that particular point, then continuing with it is correct. If you assume it's not equal to zero, sorry, not infinity, either zero or not zero. If you don't assume it's zero, then you need to consider R out. Okay, and it just so clarify what are your assumptions, and you can move forward. So that is, thank you for raising this point. Okay, so I don't want you to, anyone, I mean, to worry that about lambda, but we need to make our assumption correct. If we make an assumption and move forward correct from there, then this makes fine. I mean, whatever your answer is. Okay, thank you for this, Tuba. So this is the same relation which we just discussed earlier. Okay, now we will move to some examples. Okay, so now you can see this circuit. The input is applied from the source side and taken from the drain side. This again make it a common gate amplifier. But I have an R here, and I have this transistor here. What this one is doing here? It's basically act just like a resistor, because the gate and the drain of this amplifier, they are shorted together, so it's a diode connected. So it's similar to like if there is just any resistor here having the value of the impedance that's seen for this transistor M2, which is 1 over Gm. Again, you 2 in parallel with R out 2. You want to consider this R out 2, you don't want to consider it, both are fine. Okay, so now the circuit will look like as if there was a resistor down having the value of 1 over Gm2 in parallel with the R out 2. Now again, since not entirely Vn is reaching to the source of the amplifier, only a portion of it, we need to find or name this node as Vn. And find V out over Vn is equal to Vx over Vn multiplied with a V out over Vx. V out over Vx is simple. It's just Gm RD, the gain of the common gate amplifier, because this is what's being arrived at the gate, at the source side, and what's being reached to the V out, the amplified at the V out. It's just the gain, the simple gain GMRD. But what about Vx over Vn? Again, we will look into a voltage divider. There is a Vn coming here with Rs. So now the impedance seen from M2 contribution is 1 over Gm2, again in parallel with the R out 2. And what we see from looking up into the amplifier, we are looking from the source of the amplifier. So we will see the input impedance of the amplifier, which is 1 over Gm2. This should be clear to everybody. If it's not, please tell me. Again, yeah.
Ma'am, could you please repeat this point?
Yes, okay, I'm going to repeat it. So we have the Vn coming, the Rs, and then this node here is quite confusing. What's happening here? So if you look from this side, there is a path up and a path down. Like just two wires there are. One is going down, one going up. If you look at the down one, you find a transistor M2 that is a diode connected. This one will, it's how to say this thing. It's equivalent circuit. Yes, it's equivalent circuit of this diode connected transistor M2 is just a resistor that has a value of 1 over Gm2 in parallel with R out 2. Now, if we look up, what we see a source of this transistor M1. Now, similar thing, if you look at the source of a transistor, you will find 1 over Gm of that transistor. And that's what we have here. So the wire that's going up replaced with 1 over Gm1, and the wire that is going down M2 is replaced by its equivalent circuit, 1 over Gm2 in parallel with the R out 2. So now my task is to find how much arrived or how much being delivered at Vx from Vn. Again, it's going to be a voltage divider. So 1 over Gm1 and 1 over Gm2, if I just want to ignore the R out 2 at this moment, they are in parallel with each other. So 1 over Gm1 in parallel with 1 over Gm2 divided by Rs plus this parallel combination. Now this is all is Vx over Vn multiplied with the Gm Rd. I will get the overall gain of the V out over Vn. Any question on this? Okay. Now I think it will come further more. Yes. Any question?
And can you repeat again how we gain V out over Vx?
Okay, I'll go through it again. I didn't get which part you're asking about. But again, since there is a source impedance here and there is this resistor, not all Vn is being arrived at Vx. Therefore, we need to do it in 2 steps. First, find how much portion of Vn is arrived at Vx or at the source of the amplifier. And that's basically we did it in this step. We first have Vn with the Rx, and we looking at the input impedance of the amplifier or at the amplifier side M1. If we look at M1, we just replace that with the input impedance of the amplifier, which is 1 over Gm. Looking down at M2, we replaced it with its equivalent circuit of a diode connected transistor, which is 1 over Gm2. Therefore, it will look like this, 1 over Gm2 in parallel with 1 over Gm1. And there is Rs here, and this is Vn. And this is Vx. So how to get Vx out of Vn? Those are in parallel with each other. And 1 over Gm1 in parallel with 1 over Gm2 divided by Rs plus 1 over Gm1 in parallel with 1 over Gm2. This is a voltage divider, just how we find out from a voltage divider. Now from Vx, V out over Vx, it's just the gain of the common gate, which is GMRD. Those are all multiplied with each other. Okay?
Okay, and this GM here, which GM is this? Is it GM1 or GM2?
It should be GM1. Thank you. Yes. I mean, it's always the GM of the transistor who's making the amplification. So here it's M1, the one who's making the amplification. This transistor is the one who is making the amplification. M2 is just acting as a resistor. It's not doing anything. Okay?
Yes, ma'am, understood.
Thank you. Okay, so these are just the steps again. What do I want to do here? Yes. Again, this is a similar example. R1 and R2, they are just providing a DC point, biasing point to the amplifier. So the VB, which was earlier here, VB, this is VB, is again going to be a voltage divider, R2 over R1 plus R2 times VDD. Now somebody's saying why I'm not considering here VDD as a ground as we used to do in the small signal model. This is because I am finding the biasing points and those done in the large signal analysis. So in the large signal analysis, we don't make VDD as a grounded. Now, when I will consider again or draw a small signal model, then VDD will be as a grounded because all the DC. Sorry, I can't read the question. Yeah, we will discuss the frequencies later. At this moment, let's not just, because there is a chapter 11 that's about the frequency response of the amplifiers. We will go through it in detail. Now we'll just consider life easy and ignore about the frequencies, assuming that it's all the time going to be the same. Though this is not a realistic assumption, but at this moment, let's take the things step by step so we don't get confused. Okay, but we will come into it with very much details later, Jamshid, okay? Yes, where I were. Assuming now that this capacitor is short here, so now I want to find the gain of this stage. Now you remember M2, which was earlier in the previous example here. Now this is a similar thing, only M2 is being replaced by a resistor that's called R3, okay? And the source amplifier, the source has a resistor also of name RG. So we can do it by doing, again, naming this point Vx. So Vx over Vn, again, a voltage divider. The circuit will look like this. You will have from up direction, again, 1 over Gm1. And then there is a resistor R3, and there is RG here, and this is Vn. Same thing to what we did earlier. Now this is Vx at this point. So Vx over Vn will be again a voltage divider, 1 over Gm1 in parallel with the R3 divided by Rg plus 1 over Gm1 in parallel with R3. Now V out over Vx will equal again to Gm1 times Rd. The same thing what we did earlier. So now V out over Vn will be the multiplication of those two relations. So it will be 1 over Gm1 in parallel with the R3 divided by Rg plus 1 over Gm1 in parallel with the R3 times Gm1 Rd. Okay? Any question on this? Yes, it's the same example as we did earlier. Okay, so this is, no, it's not visible, but it's the same thing. Okay, now we're done from the common gate stage, and we will be moving to the last one that we want to discuss, which is the source follower. The source follower, how we will identify it, the input again is applied at the gate, but the output is sensed or taken from the source side. Remember that in the common source amplifier, the output used to be taken from the drain. But now in the source follower, the output is being taken from the source side, in the source follower. That's why the name is source follower. And this usually does not give us a good gain. So the gain is less than 1 or around 1. But it has its own applications. If you, sometimes it's used as a voltage buffer, like you just want to buffer the input when they have different impedances at the different location. You use this one in the middle to transfer your input without losing much of its value. Okay, so now if we want to find out the gain of this common source amplifier, again, we need to draw the small signal model. V out here. This is the source, this is the drain side, and this is the gate side. Now the drain is connected to 0. Why? Because it just here shorted to VDD, and VDD, we again replace it in the small signal model with ground. So now we need to find this out. So we have V first, V out is equal to RL multiplied with the current that is going here, which is Gm times V1 plus the current that is going through this call it I R. Now, what is this current which is called IR out? It is V out divided by R out. Now, why V out is the same as the one who's coming on the R out? Why the voltage drop across R out is also V out? Do you see this? But I think the sign should be negative. Why? Because this point is the same as V out, and the other side, so it is on one side of R out, and the other side is grounded. But the direction of the current is going into this way. That is why it should be, I think, a negative sign. I hope I'm not making some silly mistakes. Okay, and also we know that Vm equals to V1 plus V out. Okay, so now what do we want to do? We want to replace these things here. So V1 equals to Vn minus V out, and V out equals to RL times Gm. There is here Vn minus V out minus V out. I'm just replacing the relations in each location. Okay, so now we want to make all the R outs on one side, the V out. So V out 1 plus RL times Gm. This is coming from this side, and plus 1 over R out equals to Gm RL times Vn. Okay. Now how to do that further? V out over Vn is equal Gm RL over 1 plus RL times Gm 1 over R out, and this should be able to simplify it further. Simplifying it. So yes, so it should be fine. And this basically you find their parallel combination. So we will be end up having R out in parallel with RL divided by 1 over Gm plus R out in parallel with RL, just to have it in a simplified version. I mean, if you do long math, it's not the point of doing it now. We will be able to arrive from here to this relation, that R out in parallel with the RL divided, yeah, and they appear that R out is in parallel with the RL divided by 1 over Gm plus R out in parallel with RL. Yes, any question?
Ma'am, would you please explain that how does V in is equal to V1 plus V out?
Yeah, it's if you do this KVL here, you will have minus Vn plus V1 plus V out equals to 0. So V from this Vn will equal to V1 plus V out. Okay, it's just the KVL onto this loop which I just showed you here. Okay.
Yes, thank you.
Yeah, and then the rest will be just your circuit experience, and you will able to reach to this gain derivation. We just at the, I mean, we need to keep this in mind that it depends on the parallel combination of R out with RL divided by 1 over GM plus R out in parallel with RL. Now you know that GM, 1 over GM is a very small value. And therefore this approach is 1. I mean, it's less than 1, but it's very near to 1. It depends on how large R out in parallel with the RL and how small 1 over GM. But it's not greater than 1, it's smaller than 1. And that's what we want to even out. So this is the relation. Okay, now let's take this example. So this is source follower. We basically want to have Vn is applied here at the gate of the amplifier, and we are taking the output from the source. Okay, and we have V out over Vn. We need to remember that V out over Vn for any source follower is R out in parallel with the RL divided by 1 over Gm plus R out in parallel with the RL. Okay. Now here the RL has been changed. It's not a resistor RL, but we are seeing this transistor down, that is M2. And M2 here basically is, we are looking from the drain side of the M2. And therefore, what impedance do we expect to see? We expect to see R out 2. So it will be something like, so we have a resistor that is done. So this transistor M2, it's like acting like a current source with an impedance that has a value of R2. This is what we discussed in the previous class. If we are looking from the drain side, we will see an R out 2. And if we are looking from the source side of the transistor, you will see 1 over Gm. So therefore, here the RL has been replaced with R out 2. This is going to be R out 1. So the gain will be R out 1 in parallel with R out 2 divided by 1 over Gm1. Why Gm1 and not Gm2? Because the amplifier transistor is who is doing the amplification is M1 plus R out 1 in parallel with R out 2. Any question? Okay. Yes.
For example, if we take lambda is equal to 0 for M2, then ma'am, what will be the output impedance for M2?
It will be infinity. And therefore, then you may say that it's just R1 over 1 over Gm1 plus R out 1. Okay?
Yes, ma'am. Yes, thank you.
Yeah, so this is what we just did earlier. Now, the output resistance of the source follower is we are looking from this output side. So looking down, we will see RL, and looking up, we will see 1 over Gm in parallel with the R out. So quickly we can reach to that. Looking from this side, you're finding an R out up in parallel with the 1 over Gm, and down it's RL. So the final output impedance, you can prove it that it will equal to the parallel combination of R will equal to 1 over Gm in parallel with R. Okay. So this is the amplifier. Any question? Okay. Now we have a few more examples that we want to discuss. But before moving forward, any question on what we have? So at this moment, we're done from all the topologies that we want to discuss. So there is nothing, ideally, nothing new information that should be coming. only examples. So, but before going there, any question? Okay, so that's,
Ma'am, in the last example, how did you calculate R out?
sorry, in the this here, how did,
Ma'am, in the last
basic,
example.
yeah, basically you can do it with a standard way of applying a test source at the output, Vx, and having a current Ix and making the input short. And therefore, you will basically do that all work. But I'm just doing it in a quick way. You remember that we will make the VDD grounded because it's in in the DC and the small signal analysis, and we will make the input as well grounded. And we are applying a test source here. V test, sorry, or Vx and I test. Okay, so now you will see up and R out in parallel with the 1 over GM because you are looking at the transistor from the source side of M1. You are looking up into its source. So you will see this impedance 1 over GM1 in parallel with the R out one. And down, you will see RL ground. So those two resistors, they are in parallel with each other. And therefore, the current will go on, so it will be like this. Vx. As one time I call it X, one time I call it test, whichever the name you like. So this is R out in parallel with the 1 over GM1. And there is RL here. Okay, so you can easily prove it from here that Vx over Ix is the entire parallel combination of RL and R out and 1 over GM. I just did it quickly, seeing up what impedance, down what is the impedance, and their parallel combination is going to be the R out. Is it clear, Tuba, now? Okay, I hope it's clear. Okay, now let's do this example. Why slide is late? Okay, coming. So now the first step when you want to identify the gain of any stage is that you know what type of amplifier this stage is. Is it a common source? Is it a common source with degeneration? Is it a common gate or is a source follower? It cannot be any other one of those until now, like they can be only those combinations. And you should know the standard gain of each one of them. Okay, I think I lost the internet in the middle.
Yes.
Okay, that's the bad part. Let's wait for the screen to come. Again, I need to share it again. Okay, so basically, this is the example what we wanted to start with it. So the first thing again that I want to identify what stage of amplifier, what type of amplifier is this? So the input, look how I'm going to do that by looking where is the input is applied and the output is taken from which side of that transistor. So the input is being given as the here transistor and the output is taken from the drain side. Okay. Since it is this case, this means it's a common source now. Is it with degeneration or no degeneration? How do I decide this? I will look at the source side. source side is connected to VDD. This means it's in the small signal model, it will be grounded because VDD is a constant voltage. So this means it's just a common source amplifier. There is no degeneration. There is no resistor up here in the source side. So the standard gain of a common source amplifier is minus GM times RD equal with the RR transistor. Okay, now I will identify those components here. So AV is equal to...
Ma'am?
Yes. Yes.
Ma'am, your voice is breaking up a lot. We can't hear you properly.
I'm sorry about this. I don't know what is the problem. I think if you want, I can maybe stop here and record it when I get a better internet, and then I can upload it to you, and we can answer any question about it. Because I'm seeing also the internet keep disconnecting. But just need your feedback on this, if you are okay with this or not. Anyone has issue if I just do this later recorded and then upload it to you? I'll be also available tomorrow in the office hour in the morning to answer your questions, because my internet seems to be disconnecting a lot. Any objection? Okay, thank you. Then we can, I'll be happy to answer your questions. Thank you. See you later. Allah Hafiz.